Hello, today we're doing a video on the graph of a sine curve. So your note is called trigonometric functions, the graphs of sine and cosine. So we're just going to be doing anything that involves sine, and in the next video we'll talk about cosine. So this really is the fundamental video though for understanding both sine and cosine. So hopefully you really work at understanding the concepts I teach you today, and then the cosine graphing won't be as difficult. It'll just be kind of an application of what you learn in this video. So sine, remember what sine is. Sine is just the ratio of opposite over hypotenuse in a right angled triangle. Okay, so for any value of theta, so any value of an angle, it's a set number based on established ratios that were established by mathematicians hundreds of years ago. So, but what we're going to find though is that when you actually go to graph sine, so the angle is on the independent variable, and then the sine value is the dependent variable. When you actually go to graph that, it's going to create a periodic function. So sine, because it's a natural periodic function that occurs, sine and cosine are used as models to model anything that is periodic. Any motion that repeats is modeled in mathematics by either a sine equation or a cosine equation because they're periodic. So that's the general idea of what we're doing. The reason why we learn this is so that people are able to model things that are periodic, things that are repeating, things in nature, weather patterns, all kinds of different things that apply to our daily life use sine and cosine functions. So make sure you really are understanding this. Pause if you need to. I will warn you that you're going to be in it for the long haul. This is a very important concept, and this video is a bit longer, but then the cosine one won't be as long tomorrow. Okay? So first we go back to a recollection of how angles can be represented on the Cartesian plane. So any angle theta has its initial arm is on the positive x-axis, and then it will terminate on some terminal arm. This one is in quadrant 1. So we call this theta. Theta is the size of the angle. So it terminates at, let's say, has an arm there that contains the point x, y. So we can create a right angle triangle from this, where this is x and this is y, and then this part we call r, okay, which is the radius or the length of that line. Okay, now this is a right angle triangle, so we can use Pythagorean theorem. So r is just equal to the square root of x squared plus y squared. So that's, again, just from Pythagorean theorem and from our last unit. So in this case, both sine would be positive. So sine is y over r, because it's opposite over hypotenuse. So y over r. And we'll deal with cos tomorrow. Okay? So if it ends in this quadrant here, we would just put the right angle always up to the x-axis. You never attach it to the y-axis. It's always with the x. Okay? So now, I drew one in this because it's important to understand that you have a theta, which is the angle from the initial arm to the terminal arm. But then you're also going to have a beta. And beta is the related acute angle, which exists between the terminal arm and the x-axis. It's always between the terminal arm and the x-axis, never between the terminal arm and the y-axis. Never, never, never. So, in this case, you would find theta using beta. Okay? So remember that sine theta, okay, is always just equal to the absolute value of sine beta. Or actually, no, those absolute value signs should be over here. Okay? So they always have the same value. So whatever beta is, the sine of that is equal, the absolute value of sine theta is the same. It just might be positive or negative. So let's say, for instance, don't write, like this is just a little example. So let's say sine beta is 1/2. Okay, that means sine theta, in this case, because it's in quadrant 3, so our cast rule, CAST. So only tan is positive here, so then this would just be negative 1/2. So the value of what sine is determined by beta, and then the sine, that's confusing because this is sine, but whether it's positive or negative is determined by the quadrant in which it terminates. Okay, so that should be a review from last unit. All right, so then we get on to the unit circle, which is what we're going to be using in this to develop the sine curve. So you'll get down first, the unit circle is located on the Cartesian plane, centered at the origin with a radius of 1. Its equation is x squared plus y squared equals 1. Since the value of an angle and its associated trig ratios are not affected by the length of the radius, the unit circle is used to easily calculate trig ratios. So what that means is, if this is theta here, theta is going to be theta no matter how long this arm is. If this arm is 1 long or 2.5 long or √3 long, it doesn't matter. It doesn't affect how big this angle is. What matters is the ratio between the run and the rise, really, the x and the y. So the length of this does not affect or is not affected by theta at all. So that's why we make this radius equal to 1, because it's the simplest radius to use. It doesn't affect our sine values, so why not make it as simple as possible? Okay, that's the concept there. If you don't understand that, give yourself a little note and ask for clarification in person, okay, or rewatch my explanation. So in this case, our radius is equal to 1. We drop down a vertical to create our right triangle. So this is again our x value and our y value. But now we can define sine more we can define sine more simply, because sine is y over r, but now r is just 1. So really we can write that sine is just equal to y. This is extremely important, okay? To understand that sine, the value of the sine ratio, we only have to look at the y value of our coordinate. So here, if we start here, we're at 0 degrees. Here we're at 90. So for instance, as we go from 0 degrees, erase my y, up to 90 degrees, the sine ratio is the exact same as whatever the y value is as it changes. So here y is 0, and here y is 1. So in this quadrant, y, so how far we're going up, is increasing from 0 to 1. So that means that sine is increasing from 0 to 1. Okay? So that's what we're going to do on the next page. We're going to go all the way around the circle and think about what's happening to the value of y. Because whatever is happening to the value of y is exactly what's happening to the value of sine, because we've shown that sine theta is just equal to y. So here we go. Take some time to get this down, okay? So you'll notice what I've already have filled in is we're going to go around the unit circle. So we start at 0 degrees, then up to 90 degrees, 180 degrees, 270 degrees, and then one full revolution is 360 degrees. Okay? Then we're going to set up our graph. Okay, because we go 90, 180, 270, and 360. Okay, the highest our sine will ever get is 1, and the lowest our sine will ever get is -1. That's because the highest we'll ever get in our y values is 1, and the lowest we'll ever get in our y values is -1, because this is a circle with a radius of 1. You've got to remember that. So take out your calculator and let's fill in this table of values, okay? So the sine of 0, if you put it in, is just 0. Now I'm going to skip 45 and get back to that. The sine of 90 is 1. The sine of 180 is 0. The sine of 270 is negative 1. And the sine of 360 is 0. Now, in a later unit, I'll show you why this is true. If you do sine 45 degrees in your calculator, you'll get a decimal. But as an exact value, we can write it as 1 over root 2. You'll just have to trust me on that for now. And 135 is also 1 over root 2. Again, it would be the same decimal number as 45 on your calculator. 225 is negative 1 over root 2. And 315 is also negative 1 over root 2. Okay? So really I could just go from here, my table of values, to here and just plot these points, right? 0, 0, 1 over root 2, 91, etc. I could just do that. But that's not enough information for academic math. That might be enough information in a college-bound course, but in a university-bound course, we want to understand why this is happening to create our periodic motion of a sine curve. Okay, so we have to remember up here that sine theta is equal to y. Okay, that's what we have to remember when we're developing this. Okay, so whatever is happening to our y values is the same thing that's happening to our sine values. So this coordinate here, remember this is a circle with radius 1. So this coordinate, the x value is 1. And the y value is 0, okay? This coordinate, the x value is 0, and the y coordinate is 1. So this point here is negative 1, 0, and this point here is 0, negative 1. So that's an important first step, is to understand why those coordinates are what they are. Because it's a circle of radius 1. So what's happening to theta as we increase from 0 degrees to 90 degrees? Okay? So as theta increases from 0 to 90 degrees, it's okay if you write this short form, okay? As theta increases from 0 to 90 degrees, y increases from 0 to 1. So that means sine theta does the same thing. Okay? So our y value is going up, we're going higher, so our y value is going up, starts at 0 and it ends at 1. So we can label that here. At 0 degrees, okay, our sine value is 0. And at 90 degrees, our sine value is 1. And we're increasing, it's not a straight line, it's a curve, okay? Because the rate at which we're increasing y is not consistent. Okay, first it's going up really quick, then slower, and then really quick again. So that's how it looks in that section. All right, so now let's go to the next section. So from 90 degrees to 180 degrees, so as theta goes from 90 degrees to 180 degrees, what's happening? So look at what's happening to y. Y is going down because we're going in a downward direction for y. So that's the same as sine theta. So sine theta then decreases from 1 to 0. Because here y is 1, here y is 0, and we're going down from 1 to 0. So, again, here we are at 1, and by 180 we're at 0. So it's decreasing there. Okay? Now I hope you can read this orange. If not, I mean, you can listen to what I'm saying verbally. Okay, so from 180 to 270, y continues to decrease. So it's decreasing this whole time. But here we start at a y value of 0 and we end at a y value of negative 1. So theta is going from 180 to 270, and sine theta is decreasing from 0 to -1. Okay, it's at 0 and we're going down to -1. So here we are at 0, and at 270, we're at -1. Okay, and then finally, our last section here, from 270 to 360, sine theta, which again, remember, is the same as y, is going up, increasing from -1 to 0. So now we're going up. Whoop. So those are our 4 sections of a sine curve, okay? This is one cycle of a sine curve because it represents one trip around the unit circle. So this information just repeats because our angles get bigger as we continue to go around and around and around the unit circle, right? Remember that from last unit. So we can get coterminal angles to like for one here, right? By going around more than once and then ending there. So as angles get bigger, that just represents more times around the unit circle, which just repeats these cycles. So that's why sine is a periodic function. Quite a beautiful one at that. And you can also go in the negative direction by going clockwise. So from here is 0 to -90 degrees, right? The y is going down from 0 to -1. So it would be going in this direction, which we'll draw later down here. It would be going like this. So this little section, rewatch it if you need to. This is how we develop a sine curve. I can almost guarantee you're going to have to communicate your understanding of this at some point. So, as I mentioned, we can extend the graph further by continuing to cycle around the circle. And you can extend the graph for negative values of theta by going clockwise around the circle. So we have our start at 0, this is 90, okay, I should put 1 and -1. So up to 1, at 180 we're at 0, 270 we're down to -1, and then 360. So that's one pattern, but then the pattern, so I can use color here to demonstrate one cycle. And then that just repeats, right? So I go around the unit circle again. My first thing here, I'm back up at 1, back down at 0, back down at -1, back up at 0. And if you don't believe me, just put these numbers into your calculator. You'll see what the sine values are. So there, that's 2 cycles in the positive direction. Now we can go in the negative direction. If you go down 90 degrees, you're at -1. And then up another to 180, you've gone up to 0. And then keep going around to -270, you're up at +1. And then back down to -360, you're at 0 again. So it would go this way, and then it would also just continue on and on and on. So there you go, that's 3 cycles of a sine curve. I'm representing it from theta of -360 degrees all the way to theta of 720 degrees. And again, that could go on forever if you wanted it to. I think we all agree we don't want to do it forever. Okay, so what are the key features then? Back to defining a periodic function, what we already learned yesterday or last class, last video. So it's clear that sine theta is periodic. So let's draw it here again. So 0, we always go up to 1 and down to -1. We have, that's going to be 180, this is 360, so this is 90, and this is 270. So this is 180, 360. Okay, up to 1, down to 180, to 0, down to -1, up to 0. So here's so these are the 5 main points, okay? 0, 1, 0, -1, 0, da, 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 okay? If you're a musical person. So the period then is the length of one cycle. So what is that? 360 degrees. Actually, I'm going to write it in black because I think it's better. Okay, our maximum value, our highest value is 1, and our minimum value is -1. Our axis is at y equals 0, correct? So the axis is at y equals 0. Our amplitude, so the distance from the axis to the max, is equal to 1, or from our axis down to the min is equal to 1, okay? So A equals 1. Our zeros are at 0, 180, 360. So really they're at 180 times k, where k is in the set of all integers. So 180 times any integer will give you a 0. Our domain, well, you can put anything into a sine function. Actually, that should be theta, is in the set of all real numbers. You can find the sign of anything you want, positive, negative, decimal, fraction, doesn't matter. But the range, we only go up to 1 and down to -1. So our range, is y such that y is greater than or equal to -1 and less than or equal to 1. Make sure you include the equality there. But any real number in between those values. So in sketching a sine curve, remember the 5 main points, main 5 points. That's what you want to deal with. When we move on to transformations, it's always just going to be focusing on transforming those 5 points. So it's these 5 points you really need to know and understand, and they dictate the shape of the curve. Okay? And then you can continue to create more cycles by just adding a period. So you can just add 300, so if you want to get another point, you add 360 degrees and there'll be another one. If you want to get another one of these, add 360, you'll get another. If you want to get another minimum, you add 360 to this 270, you'll get another one. If you want to get another one, you just add another 360 and just keep adding periods, and you'll keep creating this function over and over and over and over again. So I know this is a lot, but now we have 2 examples of what can actually be done with this. So at this point, you may want to take a break, just kind of let your brain digest the concepts that we've just learned, or maybe you're fine to keep going. But yeah, we're moving on to the examples. So let's say I want to be able to solve if sine is equal to 2/3, and it's between -360 and 360, and we want to find all values of theta. So we've done this before. How does the curve help us with this? Well, we can use the curve to kind of show a visual of how many solutions we're going to get here. So -360, I'm just going to do -180 and -360, as well as 180 and 360, because this part isn't really part of my solution, it's just part of my understanding of the problem. So this is going to be like a rough sketch just to get my brain working here. So